Good evening from the sinister woods of Maine, and it is truly sinister today. Um, we topped out at 96 degrees at my house in Alfred, and I got to tell you, it has never been that hot in the 7 years I've lived here. The highest I have seen in Maine was when I was a kid. I was about seven, and it was 106 or 106 or 105 down in the middle of a gunquit at the pharmacy. I was like staring in disbelief that it was 105 degrees, and I have not seen anything like that for well, that's a long time ago. Anyway, tomorrow we're gunning for 100, so this will be day 3 of the heat wave, and it is truly a heat wave. It is almost unbearable to be outside, high humidity and everything like that. So, and we are also, the sky is getting very dark, and I'm guessing there's a row of thunderstorms coming through, so hopefully this doesn't get snuffed. In any case, where I left off was large igneous provinces, the lips, which I'm going to go into in great detail because that explains a lot of the sort of the final piece of the puzzle when it comes to the Permian Extinction Event. But I just wanted to touch back and remind everybody that this chart right here is showing us that within 10 million years of the Permian Extinction Event, which is right around here, the oceans are in bad shape. In other words, blue is really good, gray is not that good, and black is just awful. And really, you just kind of go with this one right here. This is basically the ocean telling us that, it was nice and lively. It slowly began to become warmer and without oxygen and probably more acidic. And then, of course, you end up getting the extinction event. And right around that time, the ocean gets so anoxic and oxygen poor that pyrite begins to form straight out of seawater, and that does not happen very often. It's happening right now in the Black Sea, and the Black Sea is very anoxic once you go down. In fact, it doesn't turn over, and that's one of the problems. That's why that happens. When I mean turnover, it means the bottom waters and the top waters do not mix, so there's no oxygen getting down to the bottom of the Black Sea. Hence, pyrite is just coming right out of the seawater and forming a layer on the bottom of the Black Sea. And what pyrite does is when it's coming out of seawater, it's telling you have very reduced conditions. There's a lot of organic matter that's not getting broken down that well. There's a lot of sulfur accumulating, and iron is being put into the oceans from the rivers, and there's heavy duty erosion going on with mafic probably. Well, they wouldn't say they're mafic, but there's definitely iron being brought into the ocean, and it's actually reacting because there's not much oxygen there. It is now combining with sulfur. So really bad conditions, and it sort of continues after the extinction event, and you can see it here. And it takes a good 8 million years or so for things to sort of start to coalesce back to normal. And I just want to flip back a couple slides, and so people can understand that this is what happened. This is a healthy ocean. This has lots of oxygen, and you have calcium carbonate organisms that can thrive. You have down here you have water that's too acidic for calcium carbonate, but that's always going to be somewhere because you end up getting acidic water down below, but a healthy ocean rotates it and you don't get a large amount of it. So you get what we call the snow line, and this is where the calcium carbonate organisms basically can thrive, and that's a healthy ocean. When we looked at the ocean prior to the extinction event, it looked like this, more or less. Very little area for things to live, mostly a very acidic ocean, probably due to higher temperatures, less oxygen, less circulation. And I'm not going to go through everything, but the gist of it is that oxygen gets brought down to the bottom of the ocean through critters, through density, hot water and cold water. Cold water will sink, and there's also particulates that go down there. But this is very important to get oxygen in the oceans. Without it, the oceans begin to die, and you have huge problems. So anyway, back to this slide. The ocean. I just want to bring everybody's attention to the oceans and the climate as a whole of Earth was going through radical changes right around the beginning around 260 million years ago, and it continued for about 10 million years until things just became abysmal. So this is a lead up to what the extinction. So in other words, if it was just purely an extinction event right at the line, you really would have seen just everything blue right up to here, and then something catastrophic happened. It didn't really happen that way. It was already leading up to it, but then something really did happen, and that's what I'm going to discuss next, and that is in the form of the Siberian Traps. The Siberian Traps begin to erupt. They are the largest known eruptive event on the Earth that we know of. May have been bigger, probably were. We just don't see it. In any case, these things were gigantic, and they put a ton of debris into the air, a ton of aerosols, probably blocked out the sun for various points in time, caused massive fluctuations with cooling and then radical heating associated with it. And even better or worse, depending how you look at it, they erupted in coal fields. Now, we know that in West Virginia, Pennsylvania, there's coal fields that have been burning for over 100 years. They can't put them out because they tunnel underground and they burn. That's my sponsor. Just kidding. So imagine, I mean, that's a tiny little, it's not really causing climate change, maybe to some extent, but these things erupted in a gigantic, like a continent size, an area the size of the United States of coal. So not only do you have volcanic eruptions, but you have them erupting in a combustible formation. So it's the worst of the worst of the worst, in a sense. So anyways, what are the Siberian Traps? Well, the Siberian Traps are a large igneous province we call a lip. And what they are is they're just massive eruptive events that show up periodically throughout history. They almost always cause problems or issues. They change the climate. They basically affect everything on the planet when they occur. The smaller ones not so much, but the really big ones are just they're game changers. They are extinction events, obviously. So basically, what happens is this looks like just like a large caldera you might see on a volcano, like say Yellowstone. Well, this does not even compare to Yellowstone, or should I say vice versa? Yellowstone does not even come close to what this is. Yellowstone would be just a tiny, it might be something like that compared to this. This is in the order of it can be almost 500, 600 miles across, maybe even 1,000 miles across. These lips, they separate continents. So the Atlantic Ocean would not be here if it were not for a lip that came up along the entire suture of Africa and North America and Asia and Europe and South America and Africa. A series of lips just broke up through that whole area. So that's in the order of like 4,000 miles, and and it's just catastrophic, and it's happened numerous times. The Siberian Traps were obviously erupted in Siberia, and they covered an area. I don't know the exact math on it, but it's safe to say that it would cover North America and Canada under a significant amount of at least probably 200 meters of lava, maybe even the United States under 2 kilometers. I'd have to actually look that up. But in any case, it's gigantic, and it is a total game changer. And the structure is quite, you have a mantle source. It comes up through. You have a plume. It starts to melt its surrounding areas. The mafic crust begins to melt, and you start to get a batch of lavas or magma chamber in here. It starts to differentiate itself. It starts to, some areas get lighter, some areas get heavier, and then it starts to basically push up the entire crust. And then it begins to cause extensional faulting here, and eventually conduits open up, and it just goes ballistic. And the good thing about these, or the bad, is that they happen in less than usually a million years. They'll put out a volume of lava that will cover the United States in less than a million years. And believe me, it sounds like a long time. It is not. Mount St. Helens is probably at least, I think it's probably close to, I'm not sure. I know that Rainier is probably older than 35 million. So, you know, these are very short-lived events, but they are catastrophic. So anyway, more about lips. So we can correlate mass extinctions to lips in a lot of places. We have talked about the big five, and they are right here. 1, 2, 3. Well, 4 would be here, and then 5. So in any case, for some reason this one isn't really lit out, but we can definitely put some correlations. The Ordovician one, there really doesn't seem to be really anything associated with it as far as a lip goes that we can tell. But there are some impact events here, so maybe this is an impact event, extinction rather. The Devonian one does have a fairly large lip associated with it. It also has numerous bolides, so this might have been a combination of two that contributed, plus smaller ones. These are impact craters. The Permian one has almost no impact events, but it has some very big eruptions, i.e. the Siberian Traps. This makes no note of the lead up, so this isn't introducing any climate change. It's just telling you the lips associated with the event. The Central Atlantic Magmatic Province is obviously associated with the opening of the Atlantic. That helped cause the Triassic-Jurassic extinction event. And then, of course, we have the Deccan Traps. Plus, there's a lot of other stuff going on in the late Cretaceous. But we have a huge amount of eruption of material come out in the Deccan Traps. Plus, we have the Chicxulub. And we all know that these two are very, everybody thinks it's just this, but it's really both of these that more likely was the cause. So there are lots of lips. 4 out of 5 patients prefer chewing a gum over dentine. I'm just kidding, I remember that commercial. But 4 out of these 5 extinctions are associated with lips. So they're a pretty good indicator that something's happening. World distribution of lips in the last 300 million years. I have maps that go back to, I don't know, 3 billion, but at that point, that's out of the scope of this. I hope I didn't do them all. If I do, I'll flip through them. Really, we want to concern ourselves with the last 300 million, and as you can see, they are very numerous. This is our one in question right here, the Siberian Traps. You know, I believe it's also over here. And actually probably encompassed an area like that, which is almost the United States, as you can see. So very large. We got some over here. This is what I'm talking about, the Central Atlantic Magmatic Province. Right here is here, 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 and here. We have, yeah, all of these reds are just Central Atlantic Magmatic Provinces. The blues are, reds are continental, flood basalts, and I know it says it's in the water here, but that's actually probably a piece of continent or flood basalt. The yellows are flood basalts, but they are silicic. The reds are mafic or basaltic. The silicic lips are rare. I'm not saying they're rare, but they're rarer. However, there are a few. I do not know the exact mechanisms causing those. They probably have to do with fractionation, or I don't know. That's sort of that's an enigma to me right now. Oceanic plateau lips. So you have plateaus where things erupt in the bottom of the ocean, and that also occurs there. You have lips. So lips are pretty big, pretty common, and pretty. These are only in the last 300 million years too. So a lot's happened in the last 300 million years. State of the Earth from deep underground to the atmosphere from 300 to 200 million years ago. This is kind of a sort of a summary of things that went on, you know, before, prior, and after the event. This is the biodiversity, so you can see life is just cranking along, a bit of a dip, cranking along, a bit of a dip, and then an absolute crash to zero. So this is your lifeline. You are healthy, you are dead right here. This is the atmosphere. This is warm to cold, so we came out of glaciation from Gondwana. We end up getting very warm, we peak, and then we end up cooling off again, but not quite as cold as we were down here. So lots of things evaporate, probably indicative of a desert climate. But as a whole, everything heated up right around the extinction event. The ocean. This is basically telling you over here has lots of oxygen, healthy ocean, and again a huge plummet right here after basically saying that the ocean was anoxic and unhealthy. This is the carbon. This is the carbon circle. This basically tells you how much carbon is being used for life. Again, a huge crash. Seawater coverage, another huge crash right here. These are the volcanism. So you have mid-ocean ridge basalt. You have an eruption here, sort of a flood basalt, but much smaller. And then you have the massive Siberian Trap, and then you have back to Morbs, mid-ocean ridge basalts. But so again, right on the money. And then we have this is the magnetic field. So you do have a reversal. This doesn't really tell us too much. I mean, it's not in the scope of my conversation, anyways. This is the transition between core wandering. Basically, you have a Paleozoic geoid, and then you have a transition to the Mesozoic geoid. Just different basic shapes, formations of the core. And then you have mantle convection, continents converging, Pangaea comes together, and then Pangaea rifts. And so, we're seeing everything's kind of connecting the dots. And Pangaea is in its heyday right here, and that's going to come into, and that's going to be explained in a little bit why that is a big problem. I'll go right back and just say it that when Pangaea comes together, as I mentioned earlier, it stops ocean circulation. And when ocean circulation stops, because it was just going right straight through that's near the equator between Gondwana and Laurasia, or Laurentia, whatever you want to call it. But once you close that off, everything's, the water got warmed in the Tethys Sea. There was no circulation. There's anoxic conditions, and Pangaea is the culprit of that. These are global temperatures over Earth's history. Colder, you have big Precambrian glaciation. You come out of it, things warm up. You get a dip here, another glaciation. Funny, these very much seem to correlate for the most part with extinction events. Big drops in temperatures generally are associated with drops in with extinction events. And you can see one right here. See another one here. Temperature drop here, not too bad. And then you have the Permian extinction. You have a small dip in temperature, but you also peak right before it. So, let's just be honest. This is as hot as it really ever got, except from the Cenozoic. There's one other time. And you're in a warm climate for most of the Mesozoic, which the dinosaurs love. And then you go back into an ice house condition here at the end of the Jurassic, into the Cretaceous, temperature drop, and then you kind of bounce around in the Cretaceous, and things start to fluctuate, and that causes problems. You have one more peak, and then we're down in an ice house today where we are. Or I should say we are in an ice house where we are today. But this is the basic trend of temperatures and their relation to extinction events. So, Pangaea, the culprit, one of them anyway. Massive amounts of erosion, tons of debris going in here. Very, very hot area right here. This is a huge hot area right around the time of the extinction event. And this is basically making the ocean in this area, without a doubt, being very anoxic and very warm, and probably very acidic. And that is actually, that will end up circulating around and contaminating the rest of the oceans as well. So this is a big problem for life. We no longer have that open seaway here. Things are getting stagnant, and when things get stagnant, life does not do well, at least the life that we had. So prior to the extinction event, we have the Devonian period here. Siberia is up here. We have Pangaea coming together, and we have a huge trench right here. And basically we're again, this water is just going through here real nicely. In fact, a lot of the continents are flooded, so life is thriving right here. Pennsylvanian period. This area now gets shut off. And now the sea really, the winds go this way, water's piling up, sea levels dropping. This is becoming probably very stagnant. The ice is melting, putting more water in, more erosion, and now the central current, central ocean current is cut off, and we're getting cold water upwelling here, which is also bringing up acidic water on the backside, and that's getting circulated. So you're getting acid from the deep ocean because of upwelling. You're getting anoxic conditions here because there's tons of sediment being washed off from these Himalaya-sized mountains. This is getting very stagnant, very acidic, and very anoxic, and very warm. 5 million years prior to the extinction event, we have giant mountains raining. Again, this has now become probably as warm as it's going to get. Maybe in another 5 million years to the event, it will go up a little bit more, but we see mountains, lots of erosion. We have deserts kind of forming around the sides. You have a trench over here. We have upwelling, still bringing up acidic water. Things are not good. So events leading up to the extinction event. Prior to Pangaea, Earth was cold, had glaciers, and had glaciers in the early Permian, meaning lots of oxygen, less carbon dioxide. Ocean circulation was efficient, and waters maintained high levels of oxygen. Prior to Pangaea, carbon dioxide was kept in check since Pangaea came together in the late Carboniferous, and large mountains locked up CO2 due to silicate weathering and kept carbonic acid out of the ocean. Life is flourishing. We know that because in the Carboniferous, that's the majority of our oil deposits and coal, and you need organic matter to do that. Now Pangaea shows up. Pangaea interrupts ocean circulation, and oceans start becoming more anoxic. Again, right here, lots water can move through. You got good circulation around the globe. Pennsylvanian period, late Carboniferous, we do not, and that's what I'm talking about. This is a problem. And then of course these mountains just continue to grow, and at this point you're really locking up a lot of carbonic acid as well as you are here. As long as these mountains are staying big, you're going to be able to remove a lot of carbonic acid. But these mountains are now starting to get lower, and carbonic acid is probably starting to get into the oceans a lot more. By late Permian, climate started warming rapidly due to influx of CO2 attributed to massive erosions, the leveling of the Pangaea Mountains, no more silicate weathering to lock up CO2, and geographical location of the continent, i.e. the CO2 which had been previously locked up by erosion of the large Pangaean mountains, or the Appalachians, or whatever you want to call them. These Himalayan-sized mountains were, because of erosion, you lock up the CO2, and you keep it out of the oceans, and you keep it out of the you keep the temperature down, and you keep it out of the air and what have you. So you have a way of keeping control of it. Once those mountains began to get leveled, there's no more silicate weathering to lock it up, and now the carbonic acid is starting to make its way to the ocean. Also, you are getting, due to the location of the supercontinent, erosion was very quick of the mountains because they were located right on the equator, just to the west of eastern flowing winds that are just going to create massive monsoons. And so the mountains weathered very quickly, kind of like the Himalayas are today. They aren't getting the influx, but they certainly are eroding because people are getting killed by avalanches all the time. And the higher the mountain, the quicker they erode. You add more water to it, well, you have a real, it is just catastrophic. There's really no place on Earth where that's going on today. If there was, we may even be cooler than we are now. In any case, when the Pangaea Mountain eroded, carbonic acid accumulates in the oceans from rivers dumping more carbonic acid into them than previous. Global temperatures begin to rise, causing more rain, accelerating oceans become more anoxic and eventually become euxinic, and then you have the formation of pyrite right out of the seawater because now you have no oxygen, so the FeO is not combining. There's not enough oxygen, so sulfur and iron are immediately they're bypassing any oxygen, and they are forming together to form pyrite, And this is all due to the lack of circulation and the mixing of deeper waters. Okay, sea levels fluctuate rapidly and generally drop. Temperatures spike near the end of the Permian, and life is already stressed in the 10 million years approaching the extinction event. So CO2 really starts to heat things up because we have no way of regulating it anymore. And once you drop the sea levels and you begin to heat things up and you get massive evaporation, well, guess what? The continents themselves, without the water around, you'll start getting very cold nights and you'll start getting very warm areas, kind of like in Africa, because there's no water. When you had early in the Permian and Carboniferous, sea levels high, so you had water all over the place regulating temperatures. You didn't have massive fluctuations, kind of like England or like Hawaii. Hawaii, it's really never too hot, never too cold. That's because the ocean's controlling it. But once all that water left, then the continent started having massive fluctuations in temperatures, and areas begin to get arid because there's no more mountains lifting up the winds, the moisture coming off the Tethys Ocean, so you're getting a desert environment now in Pangaea around the equator. So that is shocking life. It's causing huge change. So like I said, life is already stressed in the 10 million years approaching the extinction event. This is life, evolution, and sea level during the Phanerozoic. So we come out of the Ediacaran right here. We have sea level, and it really cranks up into the Ordovician, drops, comes down, and then it comes way down in the Permian. And of course, you have another drop here. Anytime sea level drops, you're almost always getting some sort of an extinction event. Here, 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 and here. They all have drops. It is universal. Siberian Traps. All right, the bad boys. So this is the size of the eruptive field. Now, all right, it's just say it. It probably goes bigger than this, and the Urals probably blocked some of it. Maybe some of it came through over here. Probably out here too. But these things were enormous. It just size does not even really put them in this. It's like just trying to describe them. But you have to understand that this is an area the size of the United States that you're looking at, and it probably filled it up to at least a kilometer thick. So huge stuff. Siberian Traps is a large region of volcanic rock known as the Large Igneous Province in Siberia, Russia. The massive eruption event that formed the traps is one of the largest known volcanic events in the last 500 million years. The eruptions continued for roughly 2 million years and spanned the Permian-Triassic boundary, or PT, which occurred 251.9 million years ago. The Siberian Traps are believed to be the primary cause of the Permian Extinction Event, the most severe extinction event in the geologic record. Subsequent periods of Siberian Trap activity have been linked to a number of smaller biotic crises, including the Smithian, Spathian, Oleocarithian, I cannot even pronounce those, extinction events. Large volumes of basaltic lava covered a large expanse of Siberia in a flood basalt. Today the area is covered by about 7 million square kilometers of basaltic rock with a volume of around 4 million cubic kilometers. Estimated to have covered the entire U.S., there it is, in 200 meters of rock. Majority of materials erupted in less than 1 million years. So it wasn't a kilometer, but it was 200 meters of rock. The entire United States. That is a lot of rock. So that is a just unbelievable amount of rock in less than 1 million years. So just think about, so 200 meters is 600 feet. 600 feet of lava across the entire United States at the minimum. Wow. Timeline of the Siberian Traps eruptive event. So we're going to go back in time to the left. You have your first eruptions right here, then you have the fissures open, and then it just continues. So 2/3 of lava volume is right here, right. The extinction event is right here. 2/3 of it came out right prior to that, and what you're looking at here is is the extinction event right here. It's between, they have it down to 61,000 plus or 61,000 plus or minus 48,000 years between 30. Okay. So they're kind of saying that this is the accepted area. The isotopes have it down between 2,100 and 18,800 years. Okay, so that's right here. This is the carbon. This is what I was telling you. This is sort of telling you what, how healthy life is. I believe that negative is bad and positive is good. The carbon-13, of course, yes, we are thriving. Huge plummet down to negative, way the hell down, into -4, and then it kind of comes back up again. It also goes negative a couple other times, and then it kind of slugs its way back. But the majority of the lava happened right in here, and then it basically heated everything up, and this is where you get the extinction event. Possible hiatus and eruption. We do know that it was still producing intrusive sills and dikes, and then the final third volume came after, and again, it looks like it caused a problem right here, but then it sort of recovered. So that's the timeline. Majority of it right before the event, causing the event, hiatus, and then continuation. So a lot of information there. So this is saying the extinction interval. So it's between 61,000. So it may have lasted 61,000 years, plus or minus 48,000 years, between 1,300 and 109,000 years. That's hard to understand. I'm not exactly sure what that means, but anyways, it's somewhere right in here. All right, eruptive event of timeline. A lot of stuff here. This is the event. This is pyroclastic explosive eruptions putting ash in the air, probably causing the atmosphere, putting CO2, causing things to pump up. We have the primary extrusion stage. This is when the majority of the lava comes out, I believe. This is the extinction event here. This is, let's see here, this would be terrestrial extinction event interval. So this is saying that this is causing terrestrial extinction. The carbon-13, healthy, takes a huge nosedive here. Another carbon-13 saying basically the same thing. Yeah, that's carbon. I don't know what the difference between these two are, but in any case, you have, so basically, at 252.3, up to that point, you have about 300,000 years of pyroclastic eruptions. Then you have the main event where you get 2/3 of the eruptive volume out. It tweaks you can tell right here, you're seeing the carbon isotopes start really moving around, which means there's die-offs, and then life rebounds, die-offs, and then you get a huge plummet. Something really just must have cranked right before here. You're getting terrestrial extinction prior to it. This is essentially saying that, yeah, this is the terrestrial extinction line. And this is just the magma, the amount of intrusive magma. I guess they have them later in different series on that, or different types of rock or different formations. But in any case, this is just showing basically that here's the extinction event. Things on land started dying at about 252.31. About 300,000 years, things really started to die. And then when you get right to the peak event, everything just goes completely haywire. It doesn't matter what graph you're looking at. So, and again, right up to the extinction event, all of a sudden, it was almost like it just had this massive pulse. It quieted down, and then it just sort of intruded underground, and then the second phase came, and it erupted the final part of it. Cross-section of the Siberian Traps over time. So this is sort of, I guess, looking down on it. But what you're looking at is 252.2. Everything's great. And then this is stage one. Stage one, part B. You have intrusive feeders or dikes coming up through. and you're starting to get a dome building here of the lava, and you're getting volcanic loading pushing down the crust. The dikes, the dikes and the feeders begin to just really start to branch out and cause sills laterally, which again, all this area under here is pretty much a coal area, so it begins to ignite in the coal. And of course, the reason why that's happening and that things are moving laterally is because the volcanic pile has solidified and it cannot punch through. Some of it still continues to punch through, but not much. And we get even more stuff going laterally, burning much wider area, really pumping gas. You're getting methane, you're getting CO2, all sorts of bad stuff being pumped. And this is stage 2. And by stage 3, the cycle has complete. You're getting some effusion up the top, but everything has intruded inside. Most of the surface or the carboniferous, the coal and everything has sort of burned itself through. So there's waning gas, and it's not quite as much to build, but there's still intrusions continuing through for quite some time, probably for the next million years or so after this occurred. But this is the problem. Greenhouse gas liberation. All that coal gets ignited in stage 2, and it just pumps so much gas in, and this causes the massive extinction event. So if you were to look at it, how did it look before? This is C. It's kind of weird. It should go A, B, C, but in going from back to forward, this is C. This is the late Permian. You got all sorts of trees, swamps, all sorts of healthy environment, rivers, critters, all that stuff. The eruptive event, you've got massive volcanic emissions, CO2, global warming, wildfires, more CO2 being pumped into the air because the coal is now releasing CO2 and it's decimating the area. And then in the early Triassic, things begin to rebound once everything. So great, catastrophic, destroys everything with fire, releases the gas, and then in the early Triassic, after 10 or 15 million years, things begin to really start to try to recover. I should rephrase that. Things start to recover fairly quickly. It just takes time to get the ball rolling. The effects on climate from the traps. Again, the carb showing you the carbon. It goes way down. There's a couple spikes, but this is the huge crash right here from it. You got another one here. You have the oxygen. Oxygen also, basically oxygen is getting burned up too in the atmosphere, so that of course drops, and these are probably from the fires. Sulfur gets pumped out because there's sulfur in the organic material that's being burned, so sulfur of course goes up. I don't know what that is. This is the ocean reducing, so obviously the ocean became very reduced, and then it slowly began to climb back. This is bad. To the right is bad. Sea level dropped, of course, probably from the evaporation of the heat. And then this is the Siberian Traps eruptive history right here. Boom. Climactic changes across the Permian Triassic boundary. What this is kind of telling you is that, you're seeing the ocean. This is the acidic ocean. The anoxic ocean. This is the negative carbon excursion. Nickel. I even mentioned that, but you have nickel kind of showing up. Where would nickel be coming from? Global expansion of microbialites, ocean acidification, the Lilliput effect. This is basically the smaller you are, the better chance you have to sort of make it. And this is a local cyanobacterial bloom. Lethal high temperatures, keep going. Local cyanobacterial bloom or interval 2. So these are the traps crossing the boundary, and these are the effects that they have. Tons of Permian stuff gone. These are the things that, things kind of, this is what happens. So in other words, none of this is happening really before to a huge extent. But once this happens, this is all the effects that it causes. And really, this is just basically saying that sea level dropped, sea level got warm, sea level got anoxic. Nickel's probably, it's probably a result of ash or deposits from the eruptions. The acidification is just terrible from it. And again, there's all sorts of stuff going on here. And of course, you have the negative carbon ice. This is just saying life is great, life is terrible, and then life is trying to get back together. So, in any case, all this is to summarize that. Once the Siberian Traps got going, Earth was already having a bad time, but once it really got going and you put tons of ash in the air, you basically pumped it with CO2. The CO2 went into the oceans as well. It basically it warmed the oceans. There wasn't turnover. Oceans became acidic. They became anoxic, and this is just basically saying, this is sort of the extent that it sort of continued. And this is all of these combined are really what are basically contributing to the mass extinction of the Permian period. And again, the temperature is goes for quite a while, lethal temperature. Effect on life forms. All right, so you've got Permian, Triassic. These are sediments right here. This is basically indicating a terrestrial extinction because you have basically things that are fairly alive and good right through here, and then everything becomes a desert. So this is indicating a terrestrial change. Land is going into desert. These are just species that either made it or did not. Let me start that over. So you have terrestrial extinction here, marine extinction here. So on land, this is what happened, and on sea, this is what happened. And so you have a very wet climate. It changes, it becomes increasingly dry, becomes a desert, and then it just becomes hot and dry and remains a very, very hot desert. We know that because sandstones, desert sandstones, are everywhere in the early Triassic. You go down here, this is what happened, and both are telling you that you have a negative carbon isotope, from the terrestrial and the land. These are the trees that ended up basically getting weaned out as things heated up. Ironically enough, these are things that began to take off. You have some things that started to actually adapt and take off. The Triassic type species right here, they made it. Of course, this is the wildfire zone, and when things really started heating up and things are burning. Tons of erosion from the mountains and what have you prior to the extinction event, as I said, from the rains, the monsoons hammering the Pangaean Mountains or the Appalachians, and in the ocean. Again, Triassic taxus starts up and it passes and it makes it. The high temperatures continue on for quite some time. Again, little things have a tendency to make it better than the larger things. Ocean acidification. Again, so this is just what this is saying, that the water became anoxic again. Wildfires. Basically, this is just stuff being dumped in the ocean from all the wildfires, and an abrupt decline of the carbon. So both sides are getting it, not just oceans, not just land, but both. Mercury sediments. This is interesting. There's a whole really good story behind this. I'm not going to go into it, but the gist of this is that no matter where you look in the globe, you are seeing high spikes of mercury. And mercury, as it turns out, is not good for anybody or anything. It causes cancer, sicknesses, you name it. It causes a lot of problems. So like nickel, heavy metals, where does the mercury come from? Well, the mercury in this case is associated with the eruptive events. Mercury comes out from the interior of the Earth, it gets into the atmosphere, and then it gets deposited, from rains or washed down from rivers or what have you. But nevertheless, with very large eruptive events like this, you tend to have mercury, and it's sure there's mercury spikes here, 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 a little bit after over here, but you get it here and here. So universally, mercury is a real problem, and there's huge spikes of it. The only way you're really going to get that is through somewhat of an eruptive event. And you know, these are saying that deeper water sediments plus shallow. So it's a good graph because it's not saying that just the shallow seems to have it a little bit earlier than the deeper a little bit later. But it's just showing that no matter where you are, you can be deep, you can be shallow, you're going to have mercury show up across on this boundary. The impacts on life forms. So Permian Extinction Event, drop. Biodiversity. Almost everything you see here, unusual facies. Well, all right. Some of these, you know, these trace fossils end up getting whacked and they get very much reduced. You can see a reduction of almost everything right here. But as you can see, they have a tendency to either make some sort of a comeback and continue on. Nothing really quite goes out on this particular graph. You're just seeing the impact of the things that the Siberian. So here's the traps. They're erupting. They just go crazy. And during this time, you're seeing the impact on these life forms. And I have to turn to the side, but radiolarians from Earthman brachiopods, yep, these all almost got whacked, but some of them did make it. Ammonoids made it, plants made it, and tetrapods. But again, all having been reduced. The tetrapods actually, they did kind of well over the cross. But again, the anoxia, this is the anoxia in the deep sea and the shallow sea, and they both existed right around the same time. So you were no place was left unscathed, more or less. Good graph. This should probably be a little bit higher, but this is not exactly jiving with my anyways. Temperature in CO2, O2 the past 4.6. So temperature fluctuates, obviously bounces around. This is our peak right here in the Permian right prior to the Permian extinction. Actually, it looks like it's peaking in the Carboniferous, but then you get another peak here, and again you get dips. And this is the oxygen. Oxygen sort of just cranked out, and then trees show up, and of course trees, when the first cyanobacterian stuff shows up, they produce, I got that wrong. Oxygen, CO2 was abundant, and then when the first land plants, or what have you, or things that can actually breathe in CO2 and produce oxygen show up, what happens is they start sucking up the CO2 and producing oxygen. That was what I was trying to say. And you know, it starts off way back here, you know, and then as you go through, right around here is when trees and land plants get going, and then you have a massive increase because they're sucking up the CO2 and producing oxygen. So oxygen levels kind of peak right at the Permian, and then they collapse and they kind of rebound back during the Mesozoic. However, CO2, you go way back here, it's at 540. This is essentially sort of the beginning of the Cambrian and the Cambrian explosion, and there's a lot of CO2 being produced right. And it probably has to do with the fact that also helped out build lots of reefs and an environment that allowed clear water and a passive margin on the east coast of North America, and it allowed life to really get its first chance. So anyway, and this also has to do with the fact that the CO2 declines as we go into Gondwana, because the polar ice caps form, and that has to happen. You cannot have a ton of CO2 in the air. So in order for ice to form on Gondwana, the CO2 had to have been getting sucked up. So, and again, I do believe that this is the onslaught of they're not land plants really until here, but there is stuff that's kind of on its way. Algae and cyanobacteria, stromatolites, what have you. These would be producing oxygen. These would be breathing CO2 and producing oxygen. So oxygen and fires. So the oxygen levels, again, they start start really cranking in the Devonian, because, like I said, you have your first land plants and stuff, and they produce oxygen. They suck up CO2 and produce oxygen, and then the oxygen levels they peak, and they sort of have a downgrade a little bit, and then they absolutely peak in the late Carboniferous, early Permian, and of course they cross the extinction event, and then they crash. So why is that? Why does the oxygen levels seem to crash right here? I don't know. This might have something to do with, this is definitely has something to do with the coming together of Pangaea. But for one reason or another, the oxygen levels begin to decline, which also contributes to oxygen not in the ocean, which also that's why that's another reason why the oceans become anoxic, because you can see oxygen is on its way down right there. So the exact reason for this, I don't know. I do know that that when CO2 goes up, oxygen has a tendency to go down. So I think this is sort of indicating that we're starting to see slight rises in CO2 as the Earth warms from the melting of the Gondwana glacial caps. So in any case, once this happens and the Siberian Traps get going, they erupt and they ignite the coal, the coal seams and the Carboniferous layers, because they erupted in basically a gigantic coal formation, and that uses up a shitload of oxygen. And so that's why this oxygen really starts to decline. So these are probably caused by some sort of an event that may have something to do with fires. But for one reason or another, oxygen gets taken down, CO2 goes up, and then oxygen really goes down and CO2 goes up here. So the effects of Siberian Traps. Take into account the climate of the Earth was already stressing life forms. Released massive amounts of SO2 and CO2 in a short time, creating a seesaw effect on global climate. Likely blocked out sunlight numerous times, slowing or halting photosynthesis worldwide. Accelerated acidification and anoxic conditions in oceans. Very bad for ocean life. Massive release of toxic chemicals, especially mercury. We find that all over the world. Eventually sent global temperatures to the possibly the highest ever seen on the planet. Not true, probably, but at least in the last 500 million years. Worse, the Siberian Traps erupted in a giant coal field that was created in the Carboniferous, making all of the above orders and magnitudes larger due to forest fires. And then the climate was driven to a barren, dry landscape, and the ocean barely able to host life. Close to 95% fatality rate. Again, I'm going back to this. It started like this, it went to this, and then it went to this. So nothing happening, beautiful, life is thriving. Everything erupts, emissions come out, CO2 gets pumped out, CO2 gets in the air, starts really warming. And then these things erupt, and you're basically releasing all sorts of way more gas, PAHs, that's Paleozoic Era hydrocarbons. We test for those when we have gasoline pollution in the ground. We always test for PAHs. And the wildfires, so you're getting CO2 from this, you're getting tons of CO2 from this, you're getting PAHs, you're also getting sulfur. It's just a mess, and then you make an environment that is basically desert-like, and then it's little by little, things start to return. Who made it? Microscopic life. I'm not going to go into this into too much detail, but let's just say, so the algae and the foraminifers, all of these got whacked. You have a few that crossed the line, and then, of course, they begin to diverge. Of the algae, really, not much of these made it, and the whole new sets basically showed up. And then it's the same thing with pterophytes. I'm not really sure what those are, but this is so you're just basically saying that microscopic life took a huge hit. Macroscopic life. Again, we've seen this. Everything got reduced. This is not showing the extinction. It's just showing the reduction in terrestrial and marine ecosystems. And as you can see, a lot when the oceans were super anoxic, nothing was really having a good time there, especially in the oceans. Mammal timeline lineage. This is kind of cool. So here's the extinction event, and this is Synapsida. This is a Sauropsida is for the reptiles, dinosaurs, what have you. But for Synapsida, which is what we are, these are the species. These went extinct prior to the extinction event. And then you have Therapsida. This is what This is what we are related to. We diverged here. These guys went extinct. This went extinct. This one made it across, but didn't make it too far. Gorgonopsids did not make it. These were probably the most fearsome predators of that time, the apex predator. And then we have another lineage where, again, most of these right to here don't make it. Well, this one made it a little bit, but it didn't make it too far. And then you have the Cynodontia. This is the guy that basically produces things that are going to evolve essentially into us. So our lineage goes here, 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 across the line here, and then it just basically just keeps going up, and then the mammalia forms. But as I said, we are related to the Dimetrodon, and there it is, right there. The Dimetrodon is, these right here, and they made it to, about 270 million years. So they had a good run. But as I said before, we are more related to this than that is to a dinosaur. Reptile and mammal divergence. Again, we come from the same. We come from an amniotes, which means it's sort of. I think that it goes to egg bearing, if I'm not mistaken. And what happens is we have a common ancestor in the Devonian into the Carboniferous, and then we split. And the sauropsids become your birds, your turtles, your dinosaurs, whatever. And then this verge of reptile becomes the synapsids, and they come the therapsids, and then the cynodonts, and then mammalia forms. This is mammals show up right about here. And then, of course, the mammals take off. We begin to diversify in the Jurassic and into the Cretaceous, staying relatively small. But then once we get once the dinosaurs get their extinction event, we begin to take over. But you can see, you got the platypus here. There's only a few of these left over. We have the yolk sac placental. This is sort of you have live young in you, but you sort of produce them, and then they crawl into a sac, and then they grow from there, and then you have the full placental. And these go all the way back right to this common ancestor. We are synapsids. The dinosaurs, the crocs, are sauropsids, but we share a very common ancestor. The tetrapod lineage chart. This is just showing. I believe tetrapod is just ability to walk on fours or whatever, and four-limbed rather. And so again, you have the common ancestor right here. You got the synapsida, the sauropsida. These go on to mammals, and then these go on to form your dinosaurs and your birds and your crocs and everything like that. And that's the timeline. So both had to make it across. This is interesting because these are, I believe, your turtles, and then these are your, look like salamanders and what have you. But again, we're not too far apart. This is our common break. We split. This is us. That is the dinosaurs and all the other reptiles and birds. And again, not a lot made it over. We were very lucky. Oh, what's interesting about this too is the metabolic rate. As you can see, the dinosaurs and the the crocs, what have you, are fairly low metabolic rate. However, and then the turtles and the salamanders, and they are super low. So like, that's why these things can hibernate and lay on the bottom of lakes and make it through the winter. The green is showing that these are fairly more active. So yeah, your crocs, your gators. Of course, the dinosaurs were fairly. They had a fairly high metabolic rate, and of course the heavier, like the Tyrannosaur, was thought to have almost like a mammalian sort of metabolic rate. And of course the birds have incredibly high metabolic rate, whereas mammals, we have a tendency to stay in the medium range. I'm sorry, I made a mistake on that. This one actually looks like it may even have, these are actually above our, like, we are basically sort of in the middle metabolic rate, whereas birds are, they're at rest, their hearts beat much faster than us. So that's basically what this is saying. Or just their metabolic rate is higher than ours. They burn energy quicker. That's why they're kind of spastic. Whereas some mammals are too. But this is just basically saying at rest, these guys, their hearts are going faster. Reptile explosion after the extinction event. So Permian, Triassic, this is just essentially showing you the few that did make it. You could sit there and break this apart into all the different species of dinosaurs, but it's just saying essentially that a few lizards or a few reptiles did make it over the line, but the divergence didn't really happen till after. So whatever was filling the niches here, when these guys went extinct, this ended up being a perfect time for reptiles. It was hot, it was dry, and when you have hot, dry, reptiles love that. This was a wet and steamy, warm area, so that's why it makes sense that things sort of going more mammalian, because mammals have a tendency to do well in those conditions, whereas the hot, dry, the reptile has a tendency to do well. And prior to this, it was the climate was kind of cool, and again, you're going to need a little bit of a higher metabolic rate to keep yourself warm. So the reptiles didn't really, they survived and they started to speed up, but they didn't really diversify until the climate and the Earth's climate was just perfect for them. And that happened as Pangaea became a very warm, or it became a very dry, hot place. And that is when the reptiles just went crazy and they diverged. And that's explained here. So this is Pangaea. You are seeing seasons now. You're seeing deserts up in here. You have hot deserts. You have warm deserts. It's just this is what the Earth looked like at that extinction event, and this is really the tropics were beginning to reduce significantly. Sauropsid and synapsid evolution. This is always kind of cool when you look at this. So the best way to look at this is how things evolved to where we are. So let's go back to our Dimetrodon. Phase 1 is parental care and locomotion. So you go from this to a Gorgonopsid. Like this was a fairly, this is very much reptile. Squatty legs out to the side, but it gets around, but it looks like a lizard. This looks like a lion crossed with a giant reptile and a hippo. This looks like something we'd see today, and it was like a giant lion, but it looked like a very primitive. It looked very primitive. It just didn't have the fine tuning that the lion does, but it's every bit in the sense looking like a gigantic predator with big fangs or big canine teeth and what have you. Then you go into something that looks again kind of reptile-ish because it's a warm, dry climate, and that's what's going to work. And then you become small. You begin to have thermoregulation. And these are when the true mammals begin to show up. They also become nocturnal because it's just easier to survive at night. And these are mammals that begin to take shape into more of the things that we see. So You start around parental care in the early Triassic, locomotion capacity, or actually it's really in the late Permian. You have thermal regulation, which means you can keep yourself warm. It starts about here. And then at phase 3, after you've gone through the Cretaceous and after the extinction event, you begin to learn how to adapt to your climate better. And so that's what the mammals we have today. They move, they can get places, they can adapt, and that's why they are the successful species of today. If you're looking at the reptiles, again, this was the reptile design. And it worked. You know, you were sort of like a crocodile. You were low to the ground. You had squatty legs, but you could move around. And then you begin to again, the same thing. You know, just took a little bit longer. Parental care starts in the early Jurassic. You have locomotion capacity. You have thermal regulation. Now this is interesting. In the Jurassic, you begin to get certain species of the reptiles that are starting to regulate themselves, and this is what evolves basically into birds. And so once thermal regulation, i.e. feathers, happens, you actually can keep yourself warm. Now flight starts to happen in the mid-Cretaceous, and then they not only can they start moving around, but now they can adapt to the climate, and these are the birds. And phase 3, of course, climate, locomotion, and adaptation. But we have very similar, you know, the reptile to mammal, the reptile to bird. Very interesting, you know, it's not too much different. Summary: the end Permian extinction is the largest known of its kind, you know, greater than 90%, and occurred roughly 252 million years ago. Although the eruptive event appears almost instantaneous in geologic record, however, it may have started up 10 million years prior. Life flourished for most of the Permian period, and almost all niches were occupied as they are today. In other words, we had things that looked like lions and acted like lions. We had things that acted like gazelles and looked like, you know, they didn't look like gazelles. They hadn't really evolved like that. They looked like big, fat, chunky, you know, sort of, I don't want to say beaked lizards, but they just didn't have the giant, you know, fangs or anything like that. You know, they were plant eaters. Life flourished for most of the Permian period, and again, almost as they are today. The Permian period started cool with some glaciation, but temperatures began to rise as the glaciers melted. As Pangaea came together, a giant mountain range occupied a large area near the equator, and due to erosion, this kept carbon levels low and temps cool. A little error right there. Yeah, shouldn't have that in. As central Pangaean mountains eroded, less carbon was locked up due to the silicate weathering and was now pouring into the ocean as bicarbonic acid. And oceans became more acidic and global temps began to rise. And it also, as the temperatures rise, the oceans become more anoxic. As global temperatures rose, ocean temperatures rose, causing oceans to become anoxic and even extinct. In some places, that means just bad, lifeless. Due to oceans becoming both acidic and anoxic, life began to struggle, and even worse, sea levels dropped worldwide, stressing life on continental shelves. As Pangaea supercontinent took shape, the climate went from a relatively stable ocean influence to land influences in many places. Sorry, another typo. The climate began to have major seasonal fluctuations, stormy weather patterns, and large desert areas forming. Due to the central Pangaean mountains being located in the equator, large storms and used causes massive amounts of erosion, sediments to be deposited inside the sea, pushing oxygen levels lower. With no oxygen to decay, it just becomes more and more basically like a black soup, and that's why we have shales, and then eventually it becomes so anoxic that pyrite forms, because the sulfur from the rotting, decaying materials with no oxygen, it cannot combine with that, so it ends up combining with iron that's in the water, and just forms pyrite. Ocean overall temperatures began to rise rapidly near the end of the Permian. Life is now very stressed, and then the Siberian Traps erupted in the late Permian, dumping massive amounts of SO2 and CO2 into the atmosphere, causing huge fluctuations in global temperatures. So you get the eruption, SO2 pumps out, temperatures drop, quickly, and then the CO2 takes over, and then they rise. You're getting up, down, up, down, up, down. Life does not like that. The Siberian Traps are the largest known volcanic eruptions to have occurred. I don't want to just say geologic times. I think there are bigger, so we're just going to say within the last 500 million years, with an estimated lava to bury the U.S. by 200 meters. They released massive amounts of toxins, most notably mercury. They also ignited the coal fields they erupted in, and which were of similar size. So a double whammy. The end result was global climate went from a wet, stable environment to a hot, dry, barren, unstable landscape in less than a few million years with equally polluted oceans. And guess what loves hot, dry climates? Reptiles, and i.e. the segue into dinosaurs. What was the likely cause of the great dying? Pangaea. Why this mass extinction matters today. So this is the modern day. You got examples of oceanic warming, anoxia, coral damage, acidification. They're all increasing worldwide because we're burning our forests, we are burning fossil fuels, and we're putting tons of CO2 in the air, and it's going right into the oceans. The nutrients from the fertilizers that we use are enhancing blooms. The algae blooms sink, causing anoxic conditions. And we have plastic pollution, and this is what's causing our oceans to die. Enlarging anoxic dead zones on continental shelves. So in other words, our most lively areas of the ocean are the continental shelves, but we are raising that dead zone. Like we said, normally a healthy ocean has a bottom layer where stuff doesn't, you don't really have a lot of living things, at least not calcium based, but there's a majority of the area is much bigger. When you start really getting acid in there, it starts to rise, and guess what? The living zone becomes very shrunken. The end Triassic seafloor spreading in the central magmatic province basically, had similar things. It warmed the climate. It dumped CO2 in the air, and again, it acidified the oceans. The CO2 is getting released through the seafloor spreading, because of the opening of the Atlantic Ocean, and it caused the same thing. So today, CO2 being pumped in causes something very similar that happened at the end Triassic. So, which also happened in the Permian. CO2 was the culprit, being pumped into the air, and it's basically getting into the oceans. And I'm going to leave it on that. This is my dog. That's Bella, and she's beautiful. And she passed away 2 weeks ago, and still very fresh in the memory and hard to deal with, but she was a wonderful dog, and I want to just dedicate this to her. And thank you for watching.